I don't want us to stop halfway here. We went through the process of solving these two linear systems, but we haven't really discussed why we did what we did. So let's go into this in more detail. For this first system, right here, I noticed that the A's were lining up, the B's were lining up, and all I need to do was bring this 13 to the other side, and now it lined up with the 5. Now, this form works really well for doing elimination quickly. So when I got to this stage here, I was able to eliminate my A. Now, let's talk about how I went from here to here. Like I had said before, we can get B so it has the same value. I would have actually tried to get a value of 6B, because then I can multiply my first by 3, my second equation by 2, and then they would line up to be 6B, 6B, and I could eliminate B. So you can choose either or. So looking here, once you get the coefficient in front of one of your variables to be the same by multiplying by different numbers, you can divide as well, you can multiply. Don't start adding and subtracting things, that's not really going to help you, but you can multiply both sides of the equation, or you can divide both sides of the equation, and that will help you be able to eliminate a variable. So I chose to go 4 minus 3. Why didn't I go 3 minus 4? You may have asked yourself that question. Well, you could do either. It doesn't matter. I chose to do 4 minus 3 so that these numbers here ended up being positive. But they both could have been negative, and they both would have canceled out, and you would have got B equals 5 either way. So it really didn't matter at all. And then we move on, and we get to this stage right here. So I have my B equals 5. I can substitute this B equals 5 into either 1 or equation 2. Doesn't matter. So I chose 2, and I got A equals negative 1. So now I have my A and my B. These are solutions that are common between the two lines. If you go anywhere else, if you change that A value, if you go, so let's go for A equals negative 2. Well, if you look at that, here's negative 2. My one line is here. My other line has a B value of what? We have a B value here. This looks to be 7. And then here, this one is going to be somewhere here. Obviously, the B values are different, right? So if I choose a different value, if I choose A equals 0, well, my one line is going to have a B value here, and my other line is going to have a B value here. They're not the same values. The A is the same for both. Both are, we're looking at the same A value, but our B's are not the same. And that goes for any A value other than the special one. Our special A value is minus 1. That is the only value for A such that both of my functions, this one and this one, are going to have the same B. That's the only A. So that's the key here. I've cleaned up the mess, and I want to now take a look at these solutions again, and then take a look at my check. So we've got solution a equals -1 and b equals 5, I want to check this. I used 2. So when I want to check, it's good form to use the other equation to just make sure when you substitute in your variables that you're going to get left side equals right side. So I chose 1. I put in my a, I put in my b into my equation 1, and here we are. We get left side equal right side. Good. We made no mistakes as far as I can tell. Our check says that to me when you get left side equals right side. If I did not get left side equals right side, that means that somewhere along the line you made a mistake in your method or through your algebra. Some kind of misstep happened. So we verified through our check. Now we know my point of intersection is at -1, 5. And we then verified this graphically by using the intercept method of determining the line here. So why didn't I move things around and do the y equals mx plus b form? Yeah, I could have. I could have changed these lines into that form, like y equals mx plus b. But I don't want to. Too much time. It's not efficient. So I know this other method. I'm just going to choose any point, really. I could choose any 2 points. But I mean, it's very easy when you do the intercepts because you're going to get a faster calculation because you're letting something be 0 here. And that goes for the second equation as well. We just found the intercepts for that. We have 2 points. That's enough to get an accurate idea of the line. Let's move on to the next question. But before we go, note that we got algebraically -1, 5, and then also visually, graphically, we got -1, 5. Same answer. That's always good. Next question. Here, we used the substitution method because, well, it's very easy to take this and substitute into our first equation. So it's very straightforward from there. Like I could use elimination, more than fine. I could just do it graphically, but you know what? If I want to do the algebra, this is a fairly efficient way of doing it. So just throw in 2 into 1, and we found this stuff and got x equals 4. You have a choice here to use equation 2 or equation 1 to solve for y. Now, 2 is much easier, so just use it. Do what's easy. So we got y equals -1. And if I substitute into 2, then I must check in 1. And as you can see here, I got left side equals right side. That tells me we're okay, we didn't make a mistake. So I was able to determine that my point of intersection is at 4, -1. Trying to graph 1, well, I use the intercept method because why would I move the x around, spend my time moving things around when I could just use the intercept method much faster. So I got x equals 5 from my x-intercept, and I got y equals -5 for my y-intercept. For 2, it's already in mx plus b form. So it's very nice to just look at my y-intercept, b, and use my slope, m, just graph it that way. And then, once again, we found a consistent 4, -1 as my point of intersection.